We're pleased to have Bruno visiting us today. So we'll talk about learning features with two layers neural networks. So maybe just some background on Bruno. So he did his PhD on string theory and decided to switch to machine learning during his postdoc. So he did his postdoc with Lenkas Deborova and Florence Sakala, if you know them. And he's been a professor at ENS since 2 years ago, and has been doing a lot of interesting work on high-dimensional statistics and two-layer neural networks and deeper neural networks. And so, please start.
Thank you to you for the nice introduction. Well, let me start by thanking Nati for hosting me here, and for Brandy for the amazing work in making this possible. Amazing admin. So today, as Theo said, I'm going to be telling you a little bit about our work on how two-layer neural networks learn features. So I thought to keep this on a high level. So yeah, if you're interested, I have some theorems, but my goal is not to go in detail over them. So if you're interested in any of that, or the technical side of that, I'm here for the whole week. I'm happy to discuss. You can go over the blackboard and so on. But I'll be a bit rushing, I think, over more of the technical aspects and trying to give you a big picture. And then, if you're interested, we can discuss later. Okay, that said, let's start. So this work, is supposed to try to make sense of this heuristic that we often hear in machine learning, in which, neural networks are good because they learn features, they adapt to the data. We say that a lot. I think, or at least we hear that a lot, and making mathematical sense of what that exactly means is not very clear. So I was discussing with Matthew just before, and I think we agree that what exactly is feature learning, how to define this precisely, is not so clear mathematically. So in this work, the goal is to try to look at simple models where we can make clear sense of what the neural network is learning and how learning these features allow it to generalize better than kernels. So, okay. So today on the manual, I'll have 3 parts in the talk. So the first part is going to be a little bit of a recap of what we know about kernel methods, or if you like to think this way, neural networks at initialization. Then we are going to move to the core of the talk, which is how neural networks are able to do better than the kernels, and how and at what cost by training or adapting over data. And then in the third part, we're going to see what the neural network learned, how does this impact generalization. So let's say the second part is just going to be about adaptativity, and the third part is going to be more about how this allows it to approximate better with a fixed data budget. Okay? So that's a lot, so let's start. Let's start part 1. Random features in kernels. So this is supposed to give you just an introduction of what I will say is not feature learning. And in particular, what kernels do. They are very efficient machine learning methods, but they are not learning features. They are more behind what is happening is some sort of feature engineering. So what are kernel methods? So let's say you have some data. Here I'm trying to introduce already some notation. So data is always going to be, for me, pairs of x and y. We're going to be focusing on supervised learning. Usually my covariates x, I'm going to assume they live in Euclidean space Rd. And then my labels is in a subset of R. Typically, I'm going to take to be R if I'm doing regression or if I'm doing classification plus or minus 1. Although most of this talk is going to be about regression. And then let's say your data is complicated and you want to find, let's say you want to classify it, so you want to find a separation. So one idea is that, by mapping this data to a higher dimensional space, it might be easier to separate it linearly. So you might find some set of a feature map that takes me from the space of covariates X, Rd, to some other space, Rp, typically of higher dimension, but not necessarily, where, in this space, data is easier to separate linearly. So, and then you would just use a linear method to fit in feature space, which typically would be some kind of empirical risk minimization. You choose a loss function, you minimize the loss between the labels, and your linear classifier, and maybe you want to add some penalty here. I'm considering reach penalty for simplicity. And then once you fit this on the data, you hope that by just using this predictor on the features, you can separate it. Now, kernels do exactly the same thing. The key idea is just that by taking the feature space to be higher dimensional, it's easier to separate it linearly. So the idea is like taking this to the extremum and then consider an infinite dimensional space. And you realize that if you want to do rigid regression in an infinite dimensional space, all that you need is a notion of scalar product. And so the right space to consider here is a Hilbert space. So you just change your scalar product for the scalar product in the Hilbert space. And then you, instead of specifying the feature map, you specify the kernel. And you can show that's a classical result in kernel theory that a well-defined kernel induces a well-defined feature map, and a well-defined feature map induces a well-defined kernel. And then what you can show is that if your kernel is good enough, so you can approximate any function if the feature space is large enough dimension, like on the limit infinite. So in particular, the closure of your Hilbert space induced by your kernel, your RKHS, spans the whole of L2 over the measure of the data. So in some sense, why I'm telling you that is just that if you have kernels and your kernels are good enough, you can fit any function in L2. So already here you've posed the problem because, if you want to say that, you are going to learn something and you're going to learn features and this is going to make you learn better in relation to what? Because this can learn everything. So essentially, what you're going to be focusing in this talk is about the cost of learning with a kernel. Because they can learn everything, but maybe it requires a lot of data. So over the past few years, interest in kernel has grown because, besides being very good methods for feeding data, it was shown by this group at EPFL and also Shizai and Bach that neural networks can be seen as kernels. So in this scaling, which is called the NTK scaling, when you take the width of the neural network to grow to infinity, you can show that around the neighborhood of initialization, things don't change a lot. And then here I'm giving an example for a two-layer neural network, but this can be generalized for deeper networks that in this large width limit, essentially neural networks stay near initialization, and near initialization they are kernel methods. And then people thought at the time that characterizing the performance of kernels could answer questions in deep learning. Then they realized that that's actually not the case. But okay, it's still let's say that motivated a lot of research in kernels over the past few years. So if you work on this field, you know what I'm talking about. And there has been a lot of theory done on kernels, including by people in the audience. So Theodore has a lot of work on that. Tang-Yu Yang here as well has a lot of work on that. Nati has work on that. I have some work on that. And here I could fill this whole slide with names. Here I have just selected some that look at what I call the exact asymptotics, which is closer to what I'm going to be talking to you about. But essentially, there has a lot of work motivated by this relationship between neural networks and kernel to try to characterize what is the performance of kernel methods at a given data budget. And one result that I think sums this all very nicely is by a paper in Theodore, Song Mei and Andrea Montanari, that tells you that if your data distribution is isotropic, for example, take a data distribution which is just uniform in the sphere, Gaussian, uniform in the hypercube, something like that, then if the number of samples and the width of your neural network scale as a power of the dimension, the best you can do with a kernel method is to learn a polynomial approximation of your target function, where the degree of the polynomial is precisely the scaling of NMP with the dimension. So it's telling you that yes, kernels are great because they can learn everything, but they require a certain data budget. In particular, if you want to learn a polynomial of degree 2 and you have P very large, you need the number of samples to be quadratic in the dimension. Okay, and this can be summarized into this figure, which I think I took from this paper by Theodore, that you see, if you have like the scaling of n, log n over d, you just, the generalization error decreases every time you get like an extra power of the dimension. Okay, so that's very nice because it tells you that, okay, for isotropic data distribution, how much data you need to learn with a kernel. And that's going to be our baseline for the rest of the talk. So behind this type of results, and here I want to give you my perspective on these things, there is something we call a Gaussian equivalence. So if we focus here on the proportional regime where n and p scale linearly with dimension, essentially you can derive these bounds by showing that the feature map of the kernel, so remember that the kernel is like a neural network at initialization. At initialization, the weights are random. So I have this feature map, sigma of wx, which is a random variable. We can show that in this proportional regime, essentially this feature map behaves statistically as if it was just a linear function of the scalar product. And this almost immediately implies the result that I showed you before. So this builds on early ideas on universality from physics, signal processing, and random matrix theory. But why we like this result very much is because it not only allows us to derive bounds, but to a very precise characterization of the generalization error of kernel methods and random features. So for instance, this is a plot that I took from one of the papers I wrote, where here you can see like the performance of the kernels, so the generalization error and the training loss of training with a kernel method with logistic regression, square loss, and you see these lines are theoretical lines. They can be described, exactly in this limit, and this is thanks to this characterization of the feature maps of kernels, because you see these are not clear like what the distribution of that is without this result, and the fact that it is just a linear function of the pre-activations make doing theory much easier. However, this is also yes. This is also what makes kernels kind of data hungry, because this Gaussian universality essentially implies an equivalence to a linear model at this regime, which implies that you have limited expressivity of these methods. So very nice is a universality result that allows us to do exact asymptotics in this regime, but on the other hand tells you that essentially your method is very limited on what class of functions it can approximate in this regime at this data budget. So yeah, so we are not happy. Gauss is not happy. So that's the takeaway number one from this talk, is that, okay, kernels are good methods because they might be able to learn everything, but they need a lot of data. And what we want to understand here in this work is how to do better. And to do better, you need to train your network. You need to move away from initialization. That's what I'm going to say. You need to learn features. You need to adapt to your data. So that brings me to the second part of the talk. Is there any question at this point before we move? Okay, good. You can ask questions during the talk. There is no problem. I keep an eye on time, but I prefer that you get something out of it than finishing all the slides that I have to show you. Okay, so to move beyond kernels and random features, we'll have to specify a particular model of data which we're interested to study. So it's very ambitious to try to characterize the generalization error of two-layer neural networks on a genetic target function like we can do for kernels. Because, well, for kernels, since they span L2, you can expand them on an orthogonal basis of the features, and it's kind of easy to do theory on the top of that. But for neural networks, it's a bit more complicated. So here we're going to be considering a specific class of data models, which is what we call a multi-index function. So we are going to assume that our labels depend on our data, so the function y given x, through some projections into some directions. So we have r directions, which I'm going to call w1 up to wr. Star means that it relates to my target. And I'm going to assume that my data distribution, so x is going to be drawn from a Gaussian distribution. Of course, relaxing that is an interesting question, but for now I'm going to put myself into this isotropic case to be able to compare to the isotropic result for kernels. And my y given x is going to depend only on our dimensional projections of the data. So, for example, for r equals to 4, you can think like a sphere, 4 directions, and then I can apply a nonlinear function on the top of that, which is this function g, that for now, it can be a generic function. So, let's look at some examples. So, the case r equals to 1 is called a single index model, and then it contains, for example, linear functions. For example, a phase retrieval problem, that is an interesting problem from a signal processing perspective. But also it can include some stochastic functions, for example, applying the error function to the pre-activation plus a Gaussian noise. So, you know, that's going to be like a probit model. And for R larger than 1, it includes also some other good friends. So, for example, a two-layer neural network can be written as a multi-index function. Is a particular example, but also includes like some kind of crazy, more general stuff. I see, Nati, you are.
I'm a bit confused. How does the, how does the stochasticity come into your model? I'm just like wondering in terms of formalism because G is determined. So I think.
Yeah. Okay. So maybe I've been a bit sloppy here. So G is not a priori deterministic.
I see.
So
for example, G is a random function.
G is a random function.
Okay,
Yeah.
fine.
G can be a random function, and this is what I try to
That's
convey
fine.
by this thing here.
Arbitrary.
So you need to compute y given x. Cool. Okay. So this is the class of target functions which you're going to be studying, and they are supposed to encompass this idea that, you know, if you get generic data, if the data is generic data in RD, you suffer on the curse of dimensionality. So learning in practice is possible, maybe because the data depends on some subdimensional, lower dimensional space, like this kind of manifold hypothesis. And so here is one way of translating this to a precise mathematical model. It depends on the data only through R-dimensional subspace. Of course, if the subspace was linear, then you just do PCA and you solve your problem. Here we are considering something a little bit more complicated. You allow for this non-linearity plus maybe some stochasticity, so that when you receive your data, it's not so easy to solve your problem by just finding these directions with PCA. And you know, these models have attracted a lot of attention in several literatures. So for example, in TCS, people have been interested in trying to compute statistical query bounds, so CSQ, SQ bounds on this class of functions. There are many works about that, so here just sampling some of them. There has been also a lot of works on trying to solve these problems in practice, like for example, using spectral methods, score functions. So these models have also been studied in this context. And in particular, these models have been studied for very long in the statistical physics literature. So starting from the work of Gardner and Derrida, who studied the perceptron model, as we call it, which is a single index model. There has been a list of works interested in that in the statistical physics literature. And here I must make a little disclaimer about this model. We are interested in trying to see how two-layer neural networks learn this low-dimensional structure on the data, how these learn these directions, right? If I was asking a different question, so if I was giving you a multi-index model and I say, solve it for me as efficiently as possible, given, for example, that the data is Gaussian or isotropic, then you would know that there are much more efficient methods to solve this problem than a two-layer neural network. So we are not trying to say you should use a two-layer neural network to solve this problem. We are interested in studying two-layer neural networks because we are interested in what happens in their dynamics. But it's good to keep in mind that if you are interested in solve a multi-index model, you can actually do it efficiently with linear sample complexity by using other methods than a two-layer neural network trained by stochastic gradient descent. That's just a disclaimer because sometimes this creates some confusion and people are not happy about studying two-layer neural networks on these models. Okay, so that's our data model. And as I hinted before, we are going to be interested in what happens when you train a two-layer neural network to learn data coming from that. And here again, I also should stress that we have a theoretical model for the data distribution, but we don't know it as a statistician, this model. Because, for example, if we knew that y given x is given by this function, you would do probably something else, a Bayesian method, for example. So this data is just to be able to take expectation over x and y when we do theory. Okay, so if we have a two-layer neural network that needs to learn this class of functions, it's clear that in order to do better than kernels, you need to learn this low-dimensional space, and you need to learn how to approximate this possibly stochastic function g, right? So the way we're going to translate this to a mathematical language is that we are going to be interested in how the weights of the network correlate with the relevant directions of the data. So as we train our model, do we obtain significant, as some people call overlap or correlation between the weights of the network and the directions which are relevant to explain it. And in particular, you're going to be interested to answer this question in a high-dimensional regime where these few directions are hidden in a very high-dimensional space. Because, of course, obtaining correlation is easier if dimension is lower, right? You just sample a random vector, and with some probability, you're going to have some overlap of order 1 over square root of d, which is vanishing when d goes to infinity. So when I tell you I'm learning something, I'm learning features, what I really mean in this model is that I mean that I'm correlating with this low-dimensional subspace. I'm making progress by training, and this training, it means that my weights are getting correlated with the relevant directions of the data. Okay?
So, Chris, how is that? I mean, another way to think about it is just: are you actually succeeding in getting non-trivial prediction in the regime where with the kernel you wouldn't be able to do anything?
Yeah.
Are those two things different, or are they the same?
Yeah, that's a good question, because okay, so as I said in the beginning, I'm going to have two parts of the talk. One is going to be about learning about how these things correlate, and the second part is it's the real question we are interested in, is how this translates into generalization. But for the first part, I'm just looking at the correlation functions, and then I'm going to be interested in how this can be translated in learning, like at lower generalization error at a certain data budget. And of course, I want to compare this with respect to the kernel that can learn something.
But I mean, if I'm succeeding, maybe just a simple question. I don't know if it's simple or not. If I'm succeeding in generalizing, does that necessarily mean I'm also succeeding in correlating, or or is that not so simple to say?
I don't know if this is an if and only if statement.
Okay.
But if you're violating like the lower bounds that Theo proved, means that you are doing better than kernels. But does this mean that you are obtaining a meaningful correlation? I believe it's okay. I need to think about it, but I believe yes, because these correlation functions are sufficient statistics for the error.
Right.
I can show that I can write the error, can be completely characterized by these functions, which means if I'm getting lower error, this must be the case. I must be getting some correlation with the directions. Yeah.
And R here is because R is fixed. R is not like growing.
R is fixed. Yeah.
Okay,
of course.
okay.
Because of course there is a very important thing to say as well, is that one particular class of functions is two-layer neural networks. A multi-index can be expressed at two-layer. So if R is exponential in D, I can
not
do any
exponential.
function.
I'm more thinking of R growing slower than D, but growing.
Yes.
No.
Okay. That's also an
Log
interesting
D
question.
or like D to the power of 0.1.
I won't be
Okay,
telling
no, sorry.
I won't be
We'll
telling
talk
you anything
later.
about that today, but that's an interesting question.
Yeah, we'll talk about
But
that later.
then you have a complexity lobe.
What?
If R grows, I think that's where you start having lower bounds on what you can do.
On which class of like lower bounds, like
Okay, let's talk about that.
Yeah.
Well, we have a whole week to.
keep sending them, because that's what I'm here for. Okay. Okay. So we talked about our data model. We talked about the hypothesis class we're going to use to fit this data. Now let's talk about algorithms. So here in this talk, I'm going to be considering doing SGD with fresh batches. So you can call this in different names, like one-pass SGD, online learning. These algorithms referred in different ways in the learning theory community. But essentially, it's going to be very important, the fact that at every step I'm taking a new fresh batch of data of size NB, and I'm going to making an update on the direction of the gradient at that. And that in particular going to mean that my gradient at every time is an stochastic variable, is an unbiased estimation of the gradient of the population. Okay, I'm going to hint of what happens if we don't do that, but it's not going to be the main topic for the day. So the key technical idea, so for now, I'm going to very soon show you some results. And these results are going to be, as I said, high level. But I want to give you a little bit of an idea of technically what is going on behind before I give you the results. So the key idea of what we're going to be doing later is that we are going to start with this algorithm. Remember, we are interested in characterizing how the correlation functions evolve. So we go from the weights to the correlation functions. So, this is an exact mapping. So this is an exact dynamics. It's also stochastic. And then what I'm going to do is that as I take some limit, d going to infinity, what happens is that you can prove that this stochastic process on the correlation functions concentrate, because these correlation functions concentrate well, into some deterministic limit described by some ordinary differential equations. So this idea of the concentration of the overlaps and effective dynamics on the space of correlation functions is a very old idea in the statistical physics of learning community. Actually, the earliest paper that I know that uses this idea is this work by David Saad and Sara Sola, Sara is not very far from here, Northwestern. But then this idea has been used in many, many other papers to characterize scaling limits of SGD dynamics for true layer neural networks, but also like, other models. Okay, so that's key idea number one. There's going to be some concentration phenomena, and then this means that all that I need to know to characterize how much correlation I'm having with the lower dimensional space is to compute these expectations. Okay, that's key idea number one. I had a key idea number two, or yeah, okay. Key idea number two is that since here my data is Gaussian, I can consider Hermite decomposition of my target function. So this is going to be very useful because, as we said, these functions are nonlinear functions. So in order to be able to say something about these expectation values that I need to characterize, it's going to be good to diagonalize them in some orthogonal basis of polynomials. So for example, if I have a single index model like just r equals to 1, I can just expand g of z into the basis of the Hermite polynomials, which you should just know if you don't know them. It's just like Hermite 3 is a polynomial of degree 3, and every Hermite k is a degree k polynomial, and they are orthogonal with respect to the Gaussian measure. Okay, and this is because my data is Gaussian. So for single index models, the sample complexity of SGD when you have batch size number 1 has been characterized by this work by Gérard Benarous and his collaborators, which tells you that essentially the number of samples that you need to learn this function when you have a single index and a single batch size depends on the first non-zero Hermite coefficient in this expansion of your target function. So essentially, since these are polynomials of degree 3, and at initialization you have like a correlation with your target function that goes like 1 over square root of d if you do random initialization, essentially you see that the complexity of building up correlation scales as the first non-zero order of this polynomial. Because the higher order, the faster this goes to 0 as d goes to infinity. And in particular, if the first coefficient is non-zero, you can learn into sample complexity proportional to the dimension. If the first coefficient is 0, but the second is non-zero, this requires d log d. And for larger information exponent, this requires d to the L minus 1 samples to learn. So for example, 10H has information exponent 1, you can check. So learning 10H takes you n proportional to d number of samples, and so on. So z squared, which is the information exponent 2, takes you d log d, and then if you have a activation which is a Hermite tree, then this will take you d squared. Okay, so that's a result from this paper. And the first result that I want to show you is like just an extension of that, because we needed to extend this to be able to answer what we want next. What happens when you have a batch size larger than 1? So essentially the answer is not much happens, right? Like in terms of sample complexity, you pay the same price as when you have batch size 1, and that's because the batches are uncorrelated. So that's very intuitive. And in terms of time complexity, you divide by the batch size, which is also an observation which is, has been made in several papers before and is a very natural thing. But we proved this in the context of these models.
So here again, you should think of NB as order 1, while D goes to, so L is fixed, NB is order 1, and D goes to
so
infinity,
here yes. So here yes.
Okay.
But I'm going to show you the result just next slide, where what happens when you take NB
with D
to scale with D.
Okay.
Yeah. And then that's gonna come. That's gonna come soon. But okay, this is very natural. It's not a very surprising result, but it's something that we needed to be able to do the discussion next. Okay, so just a summary of things. Like, if you want to learn a single index function with information exponent given by L, that's what takes you if you have batch 1, batch larger than 1, and which just means that if you can buy acceleration without compromising sample complexity if you can parallelize things. And in particular, coming to Nati's question, is that if you take the batch size to increase with D in the limit, if you tune it properly, you are able to learn the single index function in just one step. However, if you do this, you pay in sample complexity. You pay a factor D in sample complexity. So that's something you can show, and that's where I'm going to go next. I'm going to be looking at algorithms that do like just one aggressive step with large batches and large learning rate. So that's where you're going.
By the way, I think if you do log D steps, so you only need D to the L-1.
Yeah. If you do log these steps, yeah. I think you showed this, no? Or no? In one of the staircase papers.
No, I don't think.
Okay. For some reason, I thought that this was known, but maybe you can show.
It's Benarus analysis actually.
Yeah.
So you think log D you can get the optimal n. So you can get tau.
No, it's not optimal n, because the optimal n. It's okay, optimal n.
No, what Theo said now.
What you said, yeah.
So you can get the optimal n with tau equals log D. But I'm actually. Okay, I guess that answers. And then in NB equals like just the ratio of.
Yeah, the ratio. You need to be very aggressive, and also you need to be very aggressive on your learning rate. The whole thing needs to scale such that the correlation that you build is order 1 in one step. Essentially, coming back to the technical idea. Okay, so takeaway number 2 is that learning a single index function with SGD is characterized by the information exponent. This is the first non-zero Hermite polynomial in the decomposition of the target, and batch size can buy acceleration. But what about multi-index functions? So here things are going to be pretty similar to single index functions.
Sorry, Bruno, when you say it's characterized, I mean, what if that is, if you go back to the previous slide, what if this is, to what extent is this tight? I mean, is it just an upper bound?
So this is tight. You can show
online SGD.
For online SGD.
For online SGD.
Yeah. No. I'm not saying
SGD with any batch size.
Oh yeah, because as I was saying before, if you want to solve a single index model, I can give you for Gaussian data. I can give you AMP is n proportional to D. And information theoretically, that's the best you can do.
For any exponent.
For any exponent.
Okay, let's.
That's why it's important the fact that we're doing as online SGD.
Okay, but for online SGD with any batch size, if we're doing online SGD, this is optimal.
N proportional to So, sorry, can you repeat this?
Online SGD,
Yeah.
like if you never use samples
this
with any
type.
batch size, this
Yeah,
is
this type.
optimal.
Yeah. And this can be shown just by this concentration results on the dynamics and
And I'm curious, with AMP, how many iterations do you need?
order 1.
Just order one iteration?
Oh, sorry.
No.
Okay. Order D.
Just
order of D. Yeah.
Or D iterations of AMP.
Of the iterations of AMP with order D data for any.
Or is it like
Wait. Let me. Okay. So, order 1 iterations of AMP with n proportional to D. You can learn this a single index model
For NEL.
for
you
any
need a, like a
information.
spectral initialization, or
Sorry.
you need an initialization for the AMP.
Okay, so that's a subtle question. Okay, in principle, if you put epsilon correlation, you need to initialize with epsilon correlation. Yeah, but then there are non-asymptotic results, recent non-asymptotic results that waive that. But then I don't know if this is true for any single index. So I cannot tell you, but there are results on that.
I mean, it's not. But,
It's not.
Yeah, you have a condition on it.
You have a condition on the maybe you know better, like which condition on the nonlinearity you need for the non-asymptotic results from last year.
Oh, I mean, there's a lower bound on learning some single index models. There's a definition.
Okay. In any case, okay, with the Bayesian procedure where you can take as much time as you need, that's information theoretically that's n equals to D, n in proportional to D, right? So if I give you infinite compute and I allow you to do like some base optimal method, that's n proportional to D. Okay. Back to multi-index functions, and so here things are going to be exactly the same, just that instead of having like the Hermite decomposition of the target, I'm going to have some kind of tensor decomposition of my target function. And essentially all these ideas here, maybe is worth mentioning. This essentially maps the problem of learning for those of you who know, to a p-spin model, or actually to a mixture of p-spin models. So essentially, decomposing things in this base essentially maps your problem to a spin glass. And then characterizing these things for spin glass are well known. Actually, Benarus had studied the spin glass before studying that. So all these things are very natural from the statistical physics perspective. Once you have this idea that you can decompose in some polynomial, orthogonal polynomial basis. Okay. What can you learn in one step of SGD? So here I'm going to be asking myself, for multi-index functions, what can I learn if I do one single step when I froze my first layer? So my second layer is frozen at initialization. I do one step at my first layer, and I ask myself how much correlation I can build into this single step. And essentially the answer to this question is summarized into this diagram, which let's go through it now. So essentially, if you have less than these samples, you cannot learn anything. So by that, what I mean really is that the correlation goes to 0 as D goes to infinity. And you can prove that the correlation, if you have less than D samples, it goes to 0, concentrates to 0. Then, if I start to have at least D samples, I can do feature learning, so I can develop correlation with the directions of my target function. But I can show that in this regime, the best I can do is to correlate with an average direction of all the R directions. Okay, so I have these R directions, I do one step at my first layer, and I check the correlation of each of my neurons with the neurons of the target function, and I can show that they have only correlation with an average direction, and this average direction can be characterized. It's given by some average direction weighted by the Hermite coefficients. Okay? And
sorry.
Yeah.
I don't understand how that relates to it. Is this only for L equals 1, or what you just said, or for any L? This correlation with the average direction.
So this is for L large. Like so, the information exponent.
Yeah. No, for it, what you just said about correlation with the average direction.
Yeah.
That's for any information exponent, or just for information exponent 1,
No,
or just greater
it's-
than 1, or
Yeah, it's up to here. So
just
that's
for information
the,
exponent 1?
so yeah, that's the L. Yeah.
No. Yeah, I see.
And then yeah,
I mean, that's the. You said that if you have between d and d squared,
Yeah.
then you're gonna just learn a single direction.
I'm just gonna learn
And
a
that-
single direction.
That statement holds for any information exponent, or an
I need
information
I need
exponent?
I need to have at least one of the directions that has an information exponent, which is 1.
Okay, so that is only for
Yeah,
information
because
exponent
the average direction is a weighted sum
Okay.
of the directions with the weight given by the Hermite coefficient, first Hermite coefficient.
1. I see. So that's only for
Yeah.
if like.
And if I want to learn more than one direction, I need at least these square samples. And that was a known result from this paper by Alex Damian et al. So here we recover that. And if L is the first non-zero Hermite coefficient of F star, I need at least N O D to the L to be able to learn more directions. And so in particular, this is something that Theodore saw as well, like in SGD. Here is with one single gradient step, very aggressive. So this is consistent with this picture. In particular, what is interesting, it's okay. Here there is a theorem. Again, like I don't want to go over the theorem, but that's the way you can formalize it. Essentially, you want to show how much correlation is bounded away from 0 in the infinite dimensional limit, and you can characterize this exactly by bounding these correlation functions in this limit.
So quick question.
Yeah.
Is there any fundamental reason you are considering the one step SGD, or is it just because it's simpler?
Because it's simpler. Because it's simple.
And do you know anything about?
Well, so essentially, like Theodore has some nice results about that for doing several steps
Right.
of SGD. I think with learning rate, you need learning rate to be small enough, right? Yeah. So
And
and
then
the
the
picture is
proof-
similar.
It's similar.
Yeah, that's
Or is it like shifted by 1 probably?
shifted. By
Yeah, it's due
Yeah,
to the
that's
L
the
minus.
information.
Yeah, the sample complexity, yes, yeah. And in particular, okay, so this is a kind of numerical illustration of the theorem, and this is actually numerical simulation. So here we get two directions, the target function, and they are the sum of a sigma applied, the same sigma applied to the two directions. And here you have like the correlation function. So here is the correlation of each neuron. So each point here is 1 neuron, the correlation with one of these directions. And the radius here is 1 over square root of d radius. Because since we are at finite dimensions, we are actually doing simulation here. You can see at initialization, everybody's going to be around here. And then after one step, can you go away from this 1 over square root of d radius? And you can see that the sample complexity is going to depend on the degree of the nonlinearity that you choose. And here we are really choosing each nonlinearity that corresponds to a Hermite coefficient here. So okay, I'm going to move because otherwise I'm not going to be able to talk about generalization.
And just one
Yeah.
quick question about the technique to prove this result. It's just like
Yeah.
concentration.
So
to
two
the gradient
steps.
flow?
Two steps. You have concentration is the first part. So you need to prove the concentration of the overlaps of the correlation functions, and then you compute the expectation on the basis of orthogonal polynomials, and then you need to show that this is bounded away from 0 or not in the scaling that you take. So that's essentially you can do a little bit better than that, but in the worst case you need to do the simplest case you do that. Because
Okay,
you can see that the results also has some stochastic bounding of the random variables. So that's a little bit more complicated. It's actually without concentration. But the simplest version, you prove concentration and then you prove that it's bounded away from 0. Correlation function. Okay, so after one SGD step, the first layer correlates with the relevant target directions. And, that's the sample complexity that you need. And what about multiple steps of SGD? And here, again, what appears is this picture of the staircase function. So there are some class of functions which are easy to learn with SGD, with sample complexity which is linear, but they are very particular class of functions where the directions interact in a certain way. And the way they interact is given by this construction that first appears in the context of SGD in the works of Theodore, where you have this notion of staircase. So here, I can try to give you like a little bit of a intuition of what's going on. If you have a target function which has a structure such that after you learn one direction, conditionally on this direction, the other directions are linear, then you can learn them at linear sample complexity by taking several gradient steps. That's essentially the picture. So for example, this function, the first step you learn Z1, so you learn the average direction. Then condition on Z1, this function is linear on Z2, and then condition on Z2 is linear on Z3. So with 3 steps and sample complexity which is proportional, you can fully learn this type of functions. And as soon as you start having some leaps, so for example, you have Z1, so condition on Z1 is linear on Z2, and then condition on Z1, you are linear on Z3, then you learn the first average direction after 1 step, and then here you cannot learn.
I'm a bit confused. Why is there a leap?
So
In the second example, I don't think there's a leap.
yeah, there's no leap. I think this is a type function. Because this is Z1, so you should be able to learn Z3. Or I think that here you learn Z1, you learn Z2, then you need to
Z2 plus Z3.
Z2 plus Z3. So you need to look at if it is linear on the previous directions that you learned. So I think I'm not sure. I'm not sure if this is a typo. So I wanted to put a leap there, so I should have put something like.
Oh, you have a leap.
Yeah. No. Now I have a leap. Yeah. I should put some square or something there. Yeah. Okay. Yeah. I think that's a type. Because if you learn Z1, you can learn Z3. Yeah. Okay. So yeah. And if you have like leaps, then like here you learn Z1, and here you cannot learn Z2 because you have Z2 condition Z1, you have Z2 squared, so you just learn Z1 after several steps. And here you have Z1 squared, so at linear sample complexity you cannot learn anything. Okay. And again, there is a way of formalizing this into a theorem, and but I'm not going to go there. Ask me if you are interested. One thing I want to mention though is that this class of functions which are easy to learn by SGD, they are specific to online SGD. So if you change your algorithm, so in particular if you use the same sample twice, there are certain class of functions which are hard for SGD, but which can be learned by doing multiple passes over the data. So these are recent results by this bunch here, but it's something important to keep in mind, that all this discussion that I'm giving to you today is for one pass SGD where each fresh batch is independent of the previous batch of data. Okay? Yeah?
I give some intuition for this distinction.
So yeah, I can try to, I don't know if this is an intuition, but like at least it is an explanation. So essentially, when you're computing correlation functions, okay, you want to show that they are not zero in the limit d going to infinity. So when you use independent batches, some of these correlation functions, because of independence, they break into terms. And some of these terms go to zero. When you see the same batch twice, these correlation functions that you need to evaluate, they don't have independence anymore, so they are different from zero. So after 2 steps, reseeing the same data means that certain correlation functions that would go to zero if they were independent don't go to zero anymore, and then you have a non-zero correlation with the direction. So that's the technical reason. But maybe one way of seeing it is that, you know, there is this heuristic that when you do GD, it's like doing SGD, but with a covariance matrix, which is the, let's say, the empirical covariance of the data, like Mashenko-Pastur, if you have a diagonal here. So in some sense, you are like doing a structured data. You're like doing SGD on a structured data model. So you don't have these correlations going to zero anymore because of the structure. So seeing the same sample twice actually is like you are exploiting some correlations on the data, which you didn't exploit, and this helps because you are using it twice. Maybe this is an intuition. I don't know if someone has a better intuition, but that's a nice result, and I think it's good to keep in mind that these fundamental limitations of what is hard and what is not hard actually depend on the algorithm that you use. And as I said before, if you use AMP, you can do much better. If you use GD, you can also do better in the first steps. Okay. So takeaway number 4, some class of functions can be learned with linearly many steps by just a few gradient steps. These are a particular class of functions known as the staircase functions, but this construction depends on the algorithm. In particular, it's not true for gradient descent. Okay, so let me see. I have 7 minutes. Maybe with the questions that came, I can take the full time. Otherwise, I can. Should I go through the generalization part quick? I think maybe you'll be interested in that. So okay, so the theorem that we had before is characterizing the exact performance of the kernel method, and we are interested to see, like, now that you took some step or a few steps and you develop correlation with the relevant direction, how does this translate to generalization? In particular, what happens now if we train the second layer by doing ridge regression on the weights that have been trained for t steps? Okay, so that's the game. What is the generalization error? Okay. Okay, so the educated guess for this question would be, the answer would be that in the directions that I have developed correlation, I can beat the kernel in sample complexity. And in the directions that I have not built correlation, I'll do as bad as a kernel would do, or as well as a kernel would do. So for example, if I have a function of 3 directions, and at initialization, I will do as the kernel, so I would learn only a polynomial approximation of degree kappa of this function, and all the rest would be noise. If I do one gradient step, I can learn this direction. So I would be doing like using this direction plus a linear approximation of the function at this direction, and then all the rest would be like doing noise, and then so on. So if I'm able to correlate with this direction, I should expect to be able to learn better than the kernel in this direction. That's the intuition. So you have a sequential improvement over the random lazy training along the learning directions. And this can be formalized into some lower and upper bounds that essentially tell you that this educated guess is more or less correct, just that we cannot prove everything. So in particular, we cannot prove the upper bound, so it's a conjecture for now. And there is one case where we can prove this conjecture, which is the case that I want to tell you now before we finish. So remember that behind these lower and upper bounds, there is a Gaussian equivalence that tells you that because your features at initialization behave like a linear model, the best you can do is to learn a linear approximation of your function. So what we can do is that we can derive a similar Gaussian universality result, but conditionally on what you have learned. So that's why you call the conditional Gaussian equivalence theorem, and tells you essentially that your feature map at step number 1 at this linear sample complexity is going to be proportional to a linear expansion in the orthogonal directions. So you correlated with one direction plus the orthogonal decomposition. So everything on the orthogonal is going to be linear, and then the coefficients of this decomposition depend on the power of what you learned in the direction of the target. So if you learn a fraction kappa, this depends on kappa. Okay? And this made us happy because we can do now the exact asymptotics using this conditional Gaussian equivalence theorem, and we can show, so here you have like solid lines are again like the theory, and the dots are the finite size simulations. And for the same models where you can show that the going to infinite width you'd be limited by the linear kernel, you can show that you can do better than the linear kernel by taking one step. So allows us to do the exact asymptotics exactly and to provide a tight characterization of the generalization error in this regime, in the linear sample complexity regime, and after one gradient step. Of course, what happens with this equivalence as you take more gradient steps or you go to other regimes of data, that's still kind of an open question, which I find interesting. Okay, so takeaway number 5. On the learned directions, we can generalize with less data than the kernels. Okay, so I almost over of time. Let me conclude. Kernels can learn everything but require a lot of data. With one gradient step, you can do better than kernels along one and only one direction in the sample complex, like proportional sample complexity regime. With a few steps, you can efficiently learn a class of staircase functions. And the conditional Gaussian equivalence allows us to provide sharp asymptotics for the generalization error of what you can learn with a single SGD step in the proportional regime. Okay, so with that, let me thank the collaborators that appeared in the different works, because this talk is more or less like shoot-through works. So these are the great bunch that I had the pleasure to collaborate with. And I thank you for your attention. If you have more questions, happy to discuss. As I said, I'm here for the whole week. Thank you. I guess we have 1 minute. Yeah.
So, okay, I have 2 questions which might be related. So first of all, how much of this is relies on the data being exactly Gaussian, in particular completely spherical,
Yeah.
in the squared laws? So all this was just for squared laws,
Square
right?
laws, yeah.
Right. So how much are these 2 things crucial? Like if you deviate from that even a bit, like does that make it much easier or harder? I mean, it's harder to analyze, I'm sure.
Yeah.
But does it make it
Sure.
actually like easier to learn or harder to? I mean, does it?
So I think that's the elephant in the room, right? I think that one thing that I think the story is more or less the same for isotropic distributions. So spherical, cube.
Sure. I mean,
Now, if you really have like correlations in the data, my intuition is that it makes things easier because you have more information in X, right? And as a statistician, you have X, you could estimate the covariance, you could estimate the directions of X, which are more important. Now, this would depend how these directions correlates with the relevant directions of Y given X. And there is some preliminary results on that by Daniel Wu that has like this spike covariance model and show you that sometimes if they are not very well correlated, the important directions on X and important directions on Y, then it might become harder. But in general, typically, I would say that it should become easier. But the whole construction, I think, falls apart. Like the whole idea of which class of functions are hard, which class of functions are easy, even for online SGD. I guess that if you have a lot of information on X about Y, you should be able to learn in linear sample complexity, even if you have a nonlinearity which is stronger. But okay, these are guesses. Huh? I haven't looked at that. Yeah. More questions, or I think we are.
yeah, I think there.
Maybe.
Could you comment on the connection to practice?
Practice.
Second question.
That's the second elephant in the room, like, right? So I would say that in practice, data is not isotropic. So already we fall into the problem like the sub question that Nati asked before. And in practice, indeed, you don't observe all these one of the reasons why these functions are hard to learn, like these information exponent functions, is because of entropy. You are searching one direction into a high-dimensional space, and you need to find one direction among D. It's like a needle in the haystack problem. That's not the case for real data, and indeed, if you run gradient descent, this SGD on real data for a 2-layer neural networks, you see that typically you don't observe these plateau regions where you are trapped because of entropy, like the saddle-pointed initialization, if you want. So already this is, I think, is a bit shaky. Now, at least what I like to think of this is first, it's a very precise way where you can understand what is being learned and how this benefits generalization in a case where you don't have any information about X. In some sense, as at least as a bound about what is going on. Like what classes of functions are hard to learn when you don't have any you have any information on X and you just know, you just need to estimate with nothing on X y given x. I guess the real data can only be, because of what I answered to Nati, a little bit easier, because you have a lot of information on x. So y given x should be easier to learn. But yeah, it's a bit far from practice.